Let's talk about the process by which igneous rocks, solid rocks, form from magma. So specifically, let's imagine we have a pool of hot liquid magma shown by this big splotch of orange material over here. This is all liquid. And I want to consider how this thing changes into a rock by the process of crystallization of minerals, how minerals grow and form from this lava. For this magma. So remember when we talked about this earlier, we did it in the context of a diagram where we graphed the percentage of solid in the system from 0 to 100% on the y-axis versus the temperature of the magma or the rock on the y-axis. And if we think about how a material like a typical magma would cool, we started at some high temperature where it's completely liquid, 0% solid, and then as we cool it, we'll eventually reach some temperature, like right there, where the liquid begins to crystallize, starts to develop solids, and we call that temperature the liquidus. And then as the temperature decreases further, the proportion of solids in that mixture increases like this until it reaches another temperature, a lower temperature over here, we called the solidus. So the solidus represents the temperature below which there's only solids present. The liquidus represents the temperature above which there is only liquid present. And within that range of temperatures between the solidus and the liquidus here, between this range here, this is where we have both liquid and solid present. And this is the range of temperatures in which this liquid has to crystallize. So crystallization takes place within this window. This is the window where the liquids transform to the solids. So now let's go think about that, how that actually happens in a liquid. So let's go back to our liquid here and put in it a tiny crystal of olivine that is going to begin to grow. So there's our tiny crystal of olivine. It's a simple silicate mineral with iron and magnesium and silicon in it. And in order for this crystal to grow larger, I need to move onto its surface the ions that it needs to grow, and I need to move out of the way the things that it doesn't need. So moving through this liquid have to be iron and magnesium ions, right? These have to be moving through the liquid to the surface where they get incorporated into the growing crystal. And I have to simultaneously be moving away ions that aren't needed. So for example, any potassium here has to get out of the way, and any kind of aluminum has to get out of the way. And everything else that's not incorporated into a growing olivine crystal like calcium has to get out of the way. We presume that there's enough silicon present in the magma to where that's always present, but we have to get the other things out of the way, and we need to constantly be moving in the things that the olivine needs to grow. And as they're exhausted in the surrounding liquid because they get incorporated into the solid, we need to move more of it in. So the key point is that this process of moving these elements, or rather ions, through the liquid is governed by diffusion. And diffusion is a generally slow process, right? Diffusion is a slow process that is incredibly sensitive to temperature. So diffusion rates will be fast when the liquid is hot. That is, they'll be faster near the liquidus when the temperature is at a relatively high, and they will be slowest near the solidus when temperatures are low. In fact, we can show that the diffusion rate is roughly proportional to the viscosity of the liquid. Remember, the viscosity describes how fluid the liquid is. So where it is relatively fluid near the liquidus, we have fast diffusion rates. But as we approach the solidus and the viscosity drops enormously, the diffusion rates also drop enormously. So because we have a need to move things through the liquid by the process of diffusion, this window here is the only window in which we can actually grow crystals. That as we approach the solidus, these rates slow down, and when we drop below the solidus, there's no way to move stuff through the liquid or solid anymore, and so crystallization is done. So if we want to think about the process of crystallization, we have to think of it as something that happens during the time that the liquid is within this window of temperature between its liquidus temperature and its solidus temperature. So let's consider two end-member possibilities here. One, let's consider what happens with rapid cooling. So wonder what conditions would rapid cooling occur. That would occur when we take a lava flow, for example, which is very hot, and we push it out onto the surface of the earth where it's surrounded by cold atmosphere, and under those conditions with a really high geothermal thermal gradient, this thing is going to cool like crazy. And maybe this lava flow takes only a couple days to cool completely between its liquidus and its solidus. So there's only 2 days during which crystal growth can occur. And that's just not very much time. And without any time, or without very much time for growth to occur, the crystals can't grow very large. So under these conditions, what we expect to see are small crystals. Small, actually microscopic crystals are what we typically see under the conditions of very rapid cooling, because the amount of time available for crystal growth is very, very small. Now the second option occurs when we have slow cooling. And slow cooling occurs typically when that magma is sitting deeply buried inside the earth, and it's surrounded by rocks which are nearly the same temperature as the magma. So the thermal gradient is small, and this magma loses heat very slowly. A typical, say, magma body in place 10 miles down inside the earth may take 100,000 years to completely solidify. In other words, it may take 100,000 years to pass between the liquidus and the solidus, and that's a lot of time for these crystals to grow. We can diffuse a lot more stuff in and out during 100,000 years than we can in just a couple hours. And under those conditions, we expect the crystals to be able to grow to a larger size, and they typically do grow to a size where they are macroscopic. That's macro. That means they are visible to the naked eye. So the general rule of thumb is that for lavas, things which cool rapidly on the surface of the earth, rapid cooling leads to microscopic crystals. And for plutonic rocks, rocks which crystallize deep underground, slow cooling leads to large crystals, crystals that can be seen with the naked eye. Now there are 2 other comments I need to make about this, and they pertain to the phenomenon of glass. Remember I said that as crystallization rates get really rapid, as we spend very little time inside that window, there's not much time to move ions in and out of the growing crystal. Well, there may not even be any time to actually grow a single seed crystal. There may not be any time at all for any kind of organized ions to occur to create any form of crystal at all. And under those conditions, if I cool the magma rapidly enough, or lava usually, if I cool the lava rapidly enough, there won't be even enough time for little seed crystals to grow, and instead all I'll get will just be glass. So glass, the absence of crystals, is sort of the extreme case of very, very rapid cooling. So let me just put here extreme. We might get glass. Now there's one other comment that pertains to glass, however, that's very important, and that is that not all the time when we see glass, for example the rock obsidian, when we see glass, that doesn't necessarily mean that the liquid underwent very rapid cooling, because there's another factor at play here that controls the rate of diffusion of the ions in the liquid, and that is, I'll do it in a different color here, that is the water content. The water content of the liquid determines the viscosity. So that when the water content is very low, when there's very little water dissolved in the magma, the viscosity is the very low viscosity is very high. This is a high viscosity. When the water content is very low, there is a high viscosity, and a high viscosity implies a very slow diffusion rate. So under conditions where the liquid has very, very little water dissolved in it, diffusion rates can be so slow that we can end up with glass, the absence of crystals, even when there is relatively large amount of time available for, you would think, within that window between the liquidus and the solidus. For example, there are places where you can see relatively thick 10, 20 meter thick lava flows, where the interior should have taken weeks to cool, should have given us weeks of time for diffusion to occur. Yet in the interior of those flows, we see glass. And the reason we see glass is because these compositions are particularly very, very poor in water. And under those conditions with very little dissolved water, the diffusion rates are so slow that even with a couple weeks of time, there's not enough time even to grow a little seed crystal, and we end up with glass. So don't always assume that if you see glass that it must mean that the crystallization rate, that the cooling rate was extremely hot, because it can also occur with very, very dry liquids. So to summarize, though, the basic conclusion is that where we get rapid cooling, we spend very little time within that window of crystallization, and without much time, the crystals don't have an opportunity to grow very large, and we end up with microscopic crystals. This generally happens in volcanic rocks which are erupted and cool on the surface of the Earth. When we get slow cooling, which typically occurs when magmas solidify deep underground, we have lots of time within that window of opportunity between the liquidus and the solidus for crystals to grow larger, and they typically do grow larger to the point where they're visible to the naked eye. So there it is. That's the relationship between crystal size and cooling rate.